Okay, today we're going to take a look at modeling problems using variation. So the idea is that we're going to solve direct, inverse, and joint variation problems. And the idea behind variation formulas is that you have two quantities that have some type of relationship with each other. Maybe it's like your height and your body mass index, or your weight and your body mass index or something, or your weight and the amount of blood in your body. And the idea is that if one goes up and the other one either has to go up or down. So like for instance, if your height goes up, then your the amount of blood in your body will probably go up as well because you're increasing in size, so you need more blood to fill up your body. So that's just kind of the idea anyways. So that the first type of variation that we're going to look at is called direct variation, and that's where it's a variation where you have something of the form y equals kx, where k is the constant of variation, and the idea is that if x goes up, then y will go up, and if x goes down, y will go down. Okay, so if x goes down, then y must go down. If x goes up, then y goes up. Okay, so this is the easiest type of variation problem. It's called direct variation. And in any variation problem, you should always do the same thing. Write an equation that describes the given statement, and then substitute any values that are given to you to find k, the constant of variation, and then use that value k to solve any other questions that we might have. Okay, so in example 1, it says that the volume of blood B in a person's body varies directly as body weight, W. A person who weighs 160 pounds has approximately 5 quarts of blood. Estimate the number of quarts of blood in a person who weighs 200 pounds. Okay, so here we have that B must be equal to K times W, because we have a direct variation problem. Right? We say this varies directly as body weight. So B equals K times W. And then it says a person that weighs 160 pounds has approximately 5 quarts of blood. So that is 5 quarts of blood is equal to K times 160 pounds. Okay, so W was weight, B was the amount of blood you have. So you can now solve for K. You should get K as 5 over 160. Or you could write that as K is 0.03125. And as these variation problems are usually real-world problems, they tend to have some uglier numbers than what you're used to seeing, but that's fine. Okay, so again, let me just recall that B is the amount of blood in your body, and W was your weight. Okay, so now that we've solved for K, we now can solve other problems. So we have that B is equal to 5 over 160 times W. And now it asks us to estimate the number of quarts of blood in a person who weighs 200 pounds. So estimate B if the person weighs 200. So B will be 5 over 160 times 200 for 200 pounds. And so now you're going to get that B is about 6.25 quarts. Okay. Okay, it's also important to note that we could use other variables besides just y and x. So two more examples are the statement A varies directly as the square root of B. Okay, well if A varies directly to B, we would write A equals KB, but now we're saying it's A is directly varying with respect to the square root of B. So all you do is you plug in square root of B there instead. If M is directly proportional to the cube of N, then you would write M equals K times the cube of M, so that would be M cubed. Oh, sorry, N, not M. Yeah, so M is directly proportional to the cube of N. Okay. Now, we also can find relationships that are inversely proportional or inversely varying. An example of this is anything of the form y equals k over x. Okay, this is inversely proportional. Okay, and another way of looking at that is like that's y equals k times x inverse. So you're directly proportional to x inverse in this case. All right, so as a simple example, in example 2, it says y varies inversely as x, and y equals 9 when x equals 3, so find x when y is 36. So because it says that y varies inversely as x, we know that we need to start with y equals k over x, where k is the constant of variation. And then we use the initial condition that we're given. And that initial condition is that x equals 3 when y equals 9. So that allows us to solve for k. So we have y is 9 and x is 3. So k must be 27. If we multiply both sides by 3, we get 27 equals k. So now we found our constant of variation. So we must have y equals 27 over x. And then we're asked to find x when y is 36. So let's do that now. So we have, if y is 36, then we have 27 over x is equal to 36. So now we need to multiply both sides by x. We'll get 36x equals 27, or x equals 27 over 36, which is equivalent to 3/4 if you divide both sides by 9. Okay, so the answer is x equals 3/4, or 0.75. Okay, now here are two more statements that we can turn into equations. If y varies inversely as the square of x, then I think you can probably figure out what you need to do. You need to write y equals k over the square root of x. And if a varies inversely as the sum of b and c, then that would be a equals k over something. And that something is the sum of b and c, so b plus c. So it's k over the quantity b plus c. Okay. Now we can combine these variations, direct and inverse, to get what we call a combined variation. That's just an equation that has both y equals kx and y equals k over some other thing. So here's a quick example. It says that if a varies directly as b and inversely as c, where a is 7, b is 9, and c is 6, find a when b is 4 and c is 8. Okay. Oops, sorry. Right there. Okay, so we have a varies directly as b, so we need to have a equals k times b, but inversely as the square of c. So that's a equals k times b over c squared is what you should start with. That's the relationship. And now we want to use our initial conditions. So let's see, initial condition in this case. The first condition we're given is that a equals 7, b equals 9, and c equals 6. Okay, so that allows us to solve for k. Now solve for k. So we have 7 equals k times 9 over 6 squared. So it's 9 over 36. So let me see here. That means 7 equals k times, well, 9 over 36, I can divide by 9, I get 1/4. So that means k must be 28. Okay, so k is 28, and now I can use that to solve for a in the next part. So we have a equals 28 times b over c squared. Okay, and we can either write that as 28b over c squared or 28 times the fraction b over c squared. Okay, so now we're going to use this and the fact that now we're looking for when b is 4 and c is 8, and we're looking for what a is in this case. Okay, so that means that we have the equation a equals 28 times 4 over 8 squared. So it'd be 4 over 64. So a equals 28 times 4 over 64. Let's see, 4 over 64 is 1/16. So I have a is 28 over 16. And now we can simplify that a little bit more. We can divide by 2, I'd get 14 over 8. I can divide by 2 again, I'll get 7 over 4. Okay, I guess that's dividing the original thing, everything by 4 there. Okay, so a equals 7/4. Or I guess you could write that as 1.75. It would be 1 3/4. So either answer there would be fine. Okay, so that's the final answer there. Okay, so that's a combined variation problem. And next I want to look at joint variation. So joint variation is a variation in which the variables vary directly as the product of 2 or more of the other variables. So it's like combined variation, except for we're only doing direct. So it's going to be like some constant times some product of other variables. Okay, so here's an example. It says that kinetic energy varies jointly as the mass and the square of the velocity. So that means that we have let me see, let me define some variables here. So I have kinetic energy, let me call that E for energy. Okay, and then mass I'll call M, and velocity I'll call V. And so now I'm looking for a joint variation. It says that energy E varies jointly, so I know I'm going to have a K there, as the mass and the square of the velocity. So that's M and then V squared. So E equals K times M times V squared. That should be my equation. Okay, so that's just direct variation, but now we have a product M times V squared. So we have a product of more than one variable there. Okay, now once you've written down your equation, now you want to use your initial conditions. So let's look at the initial conditions. In fact, it'd be a good exercise for you to stop and read this equation or read the next sentence and look for what the initial conditions are. Maybe I'll ask a Calc 2 question about that. Okay, so we have a mass of 8 grams, so m equals 8 grams, and a velocity of 3 centimeters per second, so that'd be v equals 3 centimeters per second, has a kinetic energy of 36 ergs. So it'd be 36, and then it's ERGS, which is some type of physics thing. I think it's like what? Well, I guess it would be grams times centimeter squared over second squared would be what an erg is. Okay, so now we can use this information to solve for K. So we have 36 equals K times 8 times 3 squared. So that's 9 times 8 is 72. So K times 72 equals 36. So K must be 1/2. Okay, so we found K, that's our 1/2. And then the final sentence says, find the kinetic energy for a mass of 4 grams and a velocity of 6 centimeters per second. So we plug that K back in. So let me just rewrite what we just found. We found that E equals 1/2 times m times v squared. That's after we've solved for K. And now we're going to take this last sentence and put in the conditions to find the E. So maybe I'll do that in blue. So we don't know what E is. We know that we know that the mass is 4. So I should have 1/2 times 4 times 6 squared, the velocity squared, 6 squared. So that's okay. So we now have E should be, well, 1/2 times 4 is 2. 2 times 36 squared is 36. So I should get E is 72. And that is my final answer. Okay, so that's finding the kinetic energy for that given mass and velocity. Alright, now here's one last example where we're asked to put it all together. And so again, it's a word problem. You may need to read the prompt a few times to understand all the different pieces, but we want to define some variables and create an equation that relates them, and then we'll use initial conditions to find the unsolved variables, and then go back and answer the final question. So it says the pressure of a gas varies jointly as the amount of gas measured in moles and the temperature, and inversely as the volume of the gas. So you have to parse this sentence. We have pressure of gas, we'll call maybe pressure is P, varies jointly, so that's going to be, we're going to have P equals K times something, some product, as the amount of gas measured in moles. So the amount of mass we're measuring, maybe we'll let G be the amount of gas. So let's see here. I'm going to write these variables down. I have pressure, it's denoted by P, amount of gas, I'll denote by a G. So that's P equals Kg, and then the temperature, so that's Kgt, where temperature is T. Okay, because we said that it's jointly varying, so we know there's going to be some type of product. So it's K times Gt, and it's inversely as the volume of gas. We'll let V be volume. Okay, so we must have P is Kgt divided by V. Okay, or let me write that a little bit nicer. That's P equals Kgt all over V. So this is my relationship or my equation. P equals K times G times T, all divided by the volume V. Alright, now we want to write down some initial conditions so that we can find K. And we read the next sentence. It says that if the pressure is 936 kilopascals when the number of moles is 8 and the temperature is 260 degrees Kelvin and the volume is 960 cc's, find the pressure when the number of moles is 10 and the temperature is 270 and the volume is 600 cc's. So let's just go with the initial conditions. That was that P will be equal to 936, I think it's kilopascals, and then that's the number of moles is 8, so that's the amount of gas is 8 moles. And then the temperature is 260 degrees Kelvin, so T equals 260 degrees Kelvin. And that's K for degrees Kelvin there. And then the volume would be 960 cubic centimeters, cc's. Okay, so we use this information to solve for K. So we have 936 equals K, the constant of variation, times 8 times 260 all over 960. And so let's see, that is going to give me, if I multiply 936 times 960, I'll get 898,500 560 is equal to 2080 times k. So the 2080 is 8 times 260. So if I divide both sides by 280 or 2080, I'll get k. So I should get that k is 432. Okay, so now we can rewrite our relation with k with the update. So that's p equals 432 times gt over v. Okay. So now the last step is to solve the problem with the given conditions. So that's, it says find the pressure when the number of moles, so that'd be G equals 10, is 10. The temperature is 270 degrees Kelvin, and the volume is 600 cc's. So that's, we want to find P, so we don't know P. We know that G is equal to 10 moles. T is 270 degrees Kelvin, and let's see, V was 600. Volume was 600 cc's. Okay, so now I want P equals 432 times 10 times 270 all divided by 600. Okay, that ends up being what? P is 1944 if you plug that into a calculator. So our pressure then will be 1,944 kilopascals. Okay, so that's pretty much all there is to it. You can see that these joint variation or combined variation or direct variation and burst variation, they show up a lot in physics and in chemistry and any applied science. You're going to get lots of questions that have relationships like this. And second, they all follow the same general pattern. They're actually not that hard. Typically you're running an experiment, and we've already found that there's some type of nice relationship between these different variables, and you're just given some initial conditions. You can solve for the constant k and then use that to solve other problems with your model. All right.